All right, we're going to start rotational motion and the law of gravity, which is chapter 7. Today we are going to talk about 7.12, angular speed and acceleration. So you guys remember at the beginning of the year how we did all that kinematic stuff and you really hated it? Well, it returns to us in Greek letters for rotational stuff. Isn't that exciting? That's so exciting. Okay, so today we're going to talk about these angular displacement, velocity, and acceleration, how to calculate them, and tomorrow we'll relate them back to their linear counterparts. So first of all, we need to talk about the radian. The radian is a unit of measure. Usually you're talking about angles in degrees, but we're actually going to talk about them in radians for the first time today. A radian is about, I think, 57.3 degrees. That's how much it's about. And you can find the radian by taking the arc length and dividing it by the radius.
Oh, wow, you explained that much better than Mr. Eiderman ever could.
Well, let's not be saying that on the recording, okay?
Oh,
All right, the radian is the arc length over the radius. Now, I do not like this explanation. It's very confusing. With the picture, it doesn't look too bad, but when you're talking about things moving 6 revolutions in, so many seconds, it gets a little confusing. So this is what I actually like to do, and I can't remember if I have it on the next slide or not. I do, so I'm going to wait till the next slide to tell you. It'll be a secret until then. Oh, when S equals R, it is 1 radian. So that picture is about 1 radian. But you can find any you can find any theta, any angle here. But if it was longer, then it would be a different number. It's not going to be 1 radian. It would be 1.1 radians or something. That's a good question. I can interpret that picture real quick. Remember, red means to stop and blue means to go. Also, did you notice I was really clumsy most of the time?
'Tis known that.
Oh. So, you can't use the peps, don't use them. All right, so some more things that you would like to know about radian is 2 pi radians is equal to 360, so you can use that as a conversion from degrees to radians. That might be kind of useful. So 2 pi radians equals 360 degrees. But I find it easier to find this angular displacement, this theta, which is basically the distance it went around a circle in a radian way, is this way. The distance it went over that same distance in 1 revolution. I know that's kind of weird and kind of like because arc length is just the distance you went around the circle, and R here is radius. It gets a little confusing. But it's just a ratio, right? That's all we're talking about. And I feel like this is wrong. I think it's multiplied by 2 pi. I think that's the other thing that I forgot here. I think it's multiplied by 2 pi in the end here. I think that's right. We're going to have to double check that one. Yes.
Okay, so let's say the distance they went in some unit was 1 degree. Let's just say that. So the revolution of that same unit plus 1 would be equal to 361.
So it would be 1 over 360. Because that's how much it is in 1 revolution is 360.
Oh, I thought you were saying it's where it would be after.
No, just how much is 1 revolution. We're going to do one with the clock here in a second. I think that'll help.
Cool.
And I believe it's multiplied by 2 pi. I can't remember, but I'm pretty sure that's right. I have to look that one up, though. I have to double check that one. So I have it written down in my honors PowerPoint, so I'll double check my honors PowerPoint. I don't remember where I got this one from. Okay, so Angular displacement, that's what we're talking about here, is the axis of rotation from wherever your reference point is. If, for instance, you say your reference point is the positive x-axis on this picture, which most of the time is, it's a good place to pick just because it's pretty consistent. It doesn't matter where it is. It could have been up here. It's just like when you start your time, how far away is it from where it started? How many? And it can be, 1 revolution. So you can say it went 1 revolution. Or it could be, 4 revolutions. And if it was 4 revolutions that it went around, your distance would be 4 revolutions over 1 revolution. Times 2 pi. And that 2 pi gets it into radians. So you do need to find some sort of reference point, and this displacement, angular displacement, is a change in angle, basically. And now that you have the change in angle, which is the change in displacement in time, you can also find angular velocity, which we're going to talk about in a second.
The reference line is always 0 degrees, right?
It doesn't have to be. It could start, you could pick it from the top, because everything on that thing is rotating. So it doesn't matter where you start from.
Okay.
But usually we pick at the 0 degree mark, yes.
Wouldn't it matter where on the reference line you see the reference point?
It does. So it'll talk about the inside versus the outside, and that's why I'm having but if you're looking at angles like this, it shouldn't matter, because whether you're here or here, you still turn through 90 degrees, right? It will change the S length, which is why I like to do it this way better. And again, I'm still not sure about that 2 pi absolute, because I haven't taught this for a year. Okay, I see all blue cups, so we're going to move on. This rigid body thing is not really that important right now. Usually we've been talking about things with fixed points. So imagine like a block. Just treat it as a fixed point. Don't treat it as in mass is distributed over the whole thing. When we're talking about things with rotation, we can't treat them as points because they have to have some sort of length, because they have to have a radius. So this is what we call rigid bodies. This means that it's not going to flex as it moves. It's just going to be like a solid disc or something that's rotating. So it's not going to deform. It's not going to bend. It's not going to. It's going to move the same throughout the whole way. This is what I mean. Every point on the object undergoes the circular motion, so it's not like only spinning on the top and then not moving down here. It's not going to be moving as much, but as it goes through, it's not moving and flexing or deforming. And all points on the object rotate through the same angle. So even though they don't move as much, they're rotating through that full 90 degrees or whatever. It's really bugging me that I can't remember. Okay, are we good? We're good to go. Okay. So your angular displacement is going to be the change in this angle. So that's where your reference points comes from. It says it changed from this angle to this angle. So that change in angle is going to be your angular displacement. You can calculate this for this chapter and this chapter only. We talk about it in radians usually. For everything else, we put it into degrees. Now, in your calculator, you do not need to change to radians because we're not using the trig functions here. We're not using cosine, sine, and tangent. So you do not need to change the calculator at all. We'll just start putting radians as the unit for us. Radian is a placeholder for a unit. And like degree is a unit. Radian is kind of, like if you were to multiply like radians per second times meters, the radian disappears, sort of. It's really just a placeholder. But it's a portion of a circle. It's pretty much where the radian unit is. And now we'll talk about angular velocity, which is the change in angular displacement over the change in time. So how fast is it changing that angle?
Triangle's delta, right?
Yes, it is. Meaning change in.
I guess from the worst customer service, I'll tell you that. Delta Airlines.
Yeah, I'm pretty sure this is the right equation. This 2 pi, and it's because this is like the circumference of the circle in one revolution.
Is omega always log, or is it like...
That's omega average. This is talking about the average angular velocity.
So why doesn't it have to...
You can find an instantaneous angular velocity by doing the limit of, will be the derivative of displacement and the integral of angular acceleration.
Oh, okay, but why did... Wait, never mind.
Average.
I thought... Yeah, the simple line above.
Yeah, you could do omega with the line over average as well. That would be fine too. It's just this is the way your book wrote it. So. Okay, and so that what I was just talking about, instantaneous angular velocity is the limit of the average velocity as time approaches 0. So basically, it's the derivative of displacement with respect to time, and that's what the second one says here. And velocity is positive if it's going counterclockwise, and negative if it's going clockwise. So if you look at your clock, you can actually say that time is running backwards, right? Because it's running in the negative direction, not necessarily backwards. Or you can think of time as the clock and the time is counting down until the days of your death. Something morbid like that. Those are all the things that people have said to me. So basically, if you draw a picture, this way is positive and this way is negative. And that's true for your angular displacement, your angular velocity, and your angular acceleration. I still see one red cup, 2 red cups. You guys excited for your pep rally today? Yay!
I'm kind of excited for tomorrow, though.
Tomorrow?
Because my friend needs to
All right, angular acceleration. Average angular acceleration is taking the change in velocity over the change in time. This funny little a is an alpha. So alpha stands for angular acceleration. When you're taking just the initial angular velocity and the final angular velocity, it is an average.
Wait, pep rally? I thought we were getting free marshmallow ducks.
What? Like marshmallow ducks, like
A peep
ducks that
rally?
are shaped into, no, marshmallows that are shaped into ducks so that I can eat them.
A
Like a
peep
giant
Like
rally?
peeps?
Yeah.
Literally the most disgusting things on the planet.
See, I'm thinking that if you had some graham crackers and some chocolate and you roasted a peep over the fire, that
Or
would
in
be
a
pretty
microwave.
good.
And you would have to call animal
I'd be
control.
a chicken sandwich.
What?
It's not a duck, it's a chicken. Haven't you noticed in the chicken?
I
It's
want
not
some
even a chicken,
marshmallows.
the beaks have the right color.
The ducks.
It's supposed to be a chick.
It's supposed to be a chick, but it's not. Like, have you looked at it? It doesn't have the right facial.
True, it looks more like a little duckling.
Then again, we're arguing the artistic stylings of marshmallows. So.
That is an alpha. It existed before Jesus. What is Greek?
Alpha be like, who's your daddy?
Okay, O'Brien, are you finished with your cup? Thank you. All right. So angular acceleration, its units are radians per second squared. I didn't say that with the angular velocity, which was radians per second. So radians per second squared is your angular acceleration. A positive angular acceleration is going to be when your is in the clockwise direction or counterclockwise direction, just like with your velocities. And a negative angular acceleration is going to be in the clockwise direction, just like your angular velocities.
And I've got mathematicians because they're all like, this is how clocks work, and then this is how angulars work, so good luck with that. Here's something you're familiar to use to looking at every day. Now let's do the opposite.
I'm not sure about, actually I do know why they do that. They use the right hand rule. So you stick your thumb out of the clock and so like if you put with the clock, the way the clock moves, it moves this way. So your thumb's into the board, making it negative.
Okay.
And when it moves this way, it's going this way, so it's out of the board, making it positive. That's why.
Wait, out of the board?
Out of the board, like at you,
Oh,
making
okay.
it positive.
Okay.
And there's more stuff in it. Oh, don't you dare.
Teachers, please excuse this interruption. At this time, please release the pep rally participants that Ms. Colonna emailed earlier today. Band should report to the band room, and all other participants should report to the stadium.
Come on, please be mean.
It is an AP class.
Yeah, it's an AP class. Yeah.
I don't know if you want to show up to band late, though.
Especially what we're being recorded.
Oh.
All right, so angular acceleration.
thing.
When the object, let's see, the sign of the acceleration does not have to be the same as the sign of the angular speed. If it's slowing down, they're going to be opposite signs. If it's speeding up, they're going to be the same signs. They could be both going in the negative direction or both going in the positive direction, making it speeding up.
Here's looking at you, kid.
Instantaneous angular acceleration is going to be the derivative of angular velocity with respect to time. But again, we're not going to be doing derivatives or anything. It's just interesting to note. All right, so let's do a practice, this angular kinematics practice. We're going to find the angular displacement, velocity, and acceleration of the second hand after 4 hours. Second hand, minute hand, hour hand. So, I know you guys are so excited about this stuff.
Second hand's crazy up there.
A, the second hand, the hardest part for the second hand, well, the hardest for any of these is angular displacement. So looking at the second hand, in 4 hours, how many, in 4 hours, how many times around the clock does the second hand go?
That's here.
240?
No, it's 36, 3,000.
Wait,
600
is the
times
second
4.
clock the minute one?
No, the fastest one.
Okay.
The second hand.
How many times does it go around in 4 hours?
How many? In
In
4
4
hours.
hours.
In 4
Oh,
hours. So our time is 4 hours here.
Times 4.
I don't know why they were talking about the first, second, and third hand.
14,400.
That's what I thought.
Thank you.
Wait, no. How many times does it go around?
Okay, it goes around 60 times in 1 minute, and then
60 times.
60 times. There's 60 minutes in an hour, and then it's going 4 hours, right? So multiply these things all together,
Oh,
right? So 60 times 60 times 4, 3,600 times 4.
doesn't it only go around once?
It's
Oh, yeah,
14,400.
It's actually.
Okay, wait.
Yeah.
Stop.
I know. I was like, I'm like,
It's 20. It's 240.
Stop. We got an extra.
Okay.
So 240. Okay, and that's so it makes 240 revolutions. And how many revolutions are there in one revolution?
One.
That's in 40 minutes.
One revolution.
That's in 4 minutes.
What does that do for us?
No, that's in 4 hours.
No, number
Because-
second hand makes a minute.
oh no, it is the
We were calculating
number.
seconds. We were calculating seconds, not.
I'm pretty sure it is times 60. I think you're right.
It's 14,400.
Yes.
Because if it
Because
goes,
we're thinking of the minute hand, not the
it goes-
second hand.
Oh, yeah.
So the second hand is.
No, the second hand
So it
doesn't
goes-
go around the clock in 1 second. It goes around 60 times.
60 seconds to
Yeah.
1 minute.
Yeah.
Wait,
Which
an hour.
Minutes.
times 4. So it's
One.
240.
No,
but it doesn't. You don't multiply it by 60 again.
Oh, because it doesn't make a revolution.
Yes, you do. 60 seconds
Yeah,
goes
no.
60 minutes.
Yeah, but it doesn't make a revolution in 1
Silence! My authority shall be recognized.
Your what?
Second hand goes around 60 times in 1 hour.
Yes.
Minute hand goes around once an hour.
Yes.
The hour hand goes around once every 24 hours.
Yes.
It's once every 12 hours.
These are the whatever. These are the universal truths, and they shall be accepted.
Until we get clocks that are shaped like
Are we
ours.
okay with that?
Yes.
Okay. 240 revolutions. How many revolutions are in one revolution?
One.
One.
And multiply that by 2 pi. Because that's what our equation is.
So 485. Negative. Gotta remember that it's negative.
It is negative. Good job. All right, so there's your angular displacement. Now let's find velocity, angular velocity. What is that going to be? How do I set up the equation for that?
It's
Displacement, right?
it's 2 pi radians per minute.
Jumping ahead. All right, so you take the displacement, so from where it started from 0 to 4 hours, it's going to go that much displacement. And what's the time for this? 4 hours. How many seconds is that?
Wait, why are we doing seconds?
Because it's got to be radians per second.
Now that one's the big number.
That's the 1440 number, or the 14,040 number.
Yep.
Okay, and what does that give us as an answer?
A really tiny number.
What's that really tiny number?
1/30th.
Can you give me a decimal?
0.0333.
Pi over 30 rather.
30.
Radians a second.
Why would we do that?
Because the SI unit for these are radians a second.
I mean, why would we make it a decimal?
Oh yeah, you could do 1/30th. That'd be fine.
Wait,
Just
so
It's
you
actually,
count
it's
pi
pi
too?
over 30.
pi over 30.
Yeah.
I like decimals better. That's why I do them. I know.
Oh wait, we're missing pi.
I'm really confused. Do we put
It's,
pi in
we
this?
didn't. It's
Oh,
actually, it's
okay.
actually.
Don't we have to multiply?
No, I didn't multiply pi though.
Oh, so
I like
it's
pi. I just like pi.
Dude.
I like that. You have to multiply.
okay. And what is its angular acceleration?
The Jesus fish.
Hold on.
So it's that over time. So
Yep.
it's that one. Yeah.
Does the second hand speed up?
No. But so
It ticks at a constant velocity the whole time with 0.
okay.
Because this is constant. So tricky, huh?
Yay.
Okay, let's do B. How about you guys do B?
Okay. So it's the theta is 4. Actually 8 pi.
On your paper.
Negative.
No, talk it out. I don't want to hear it. You talk it out after you find the answer, and we'll all talk to it together. And we've got 5 minutes left, so we probably won't get any clicker questions today, but we'll at least get through this, and that will help you a lot. Because the hardest part here is figuring out what theta is. But if you use this, you should be fine. And I do believe at the pep rally they'll be releasing you to the buses right after the pep rally, so make sure you bring your stuff. You need to stop by your locker and pick up your stuff. But I'm not exactly sure, but I'm pretty sure that's what they're going to do.
Well, so for B, like for theta, wouldn't it still be 60 times 4?
No? Because you're talking about the minute hand now. How many times does the minute hand go around in 4 hours? How many times does the minute hand go around in 1 hour?
60.
The minute hand?
Oh, no.
After 1 minute, the minute hand only moves lightly.
In an hour?
In an hour.
Once.
Once. Okay, and then over 4 hours, how many times are going to go around?
4.
So the top is only 4.
Okay.
So it makes 4 revolutions in 4 hours.
You have to change, or when you're finding the average velocity, you have to change it to minutes.
Should be in seconds, radians per second. And I want you to do C, too. Again, I'm looking mostly at displacement here. Displacement's what I'm interested in. Because the omega is really easy. The angular velocity is fine. So C, what would you do? It's not as easy, right? Okay, what'd you do?
Since it goes a third of one revolution around, I did negative 1/3 times 2 pi.
Okay, that's one option. Here's what I do. I look at the little sections on the clock, right? There's 12 little sections on the clock.
4/12.
In 4 hours, it goes 4 sections, and there's 12 sections in 1 revolution. Does that make sense?
That is
So it goes 4/12 around. So when it goes 4 little sections, and there's 12 sections in 1 revolution. So that's what I did.
That is a very solid way of doing it.
And that gives me 2/3 pi. Radians. Any questions? No? All right. Go ahead and put your clickers and your cups away, and we will get our stuff ready for the pep rally.